Hi there everybody, this is Matthew speaking from Mazebolt. Today we're going to be looking at and understanding how the recent NTP DDoS attacks have been happening. There's been a lot of media reports that NTP DDoS attacks have been reaching 400 gigabits. We're going to have a look at how these attackers are able to get such high bandwidth attacks that obviously weren't seen in the past. We're going to start off by looking at the NTP protocol itself. NTP stands for Network Time Protocol. We'll have a look at what that protocol is. The attack vector itself, there's a type of attack vector that the NTP DDoS attack uses, and we'll see why it's so effective. We'll look at another piece of the puzzle called BCP 38, which is the Best Current Practice 38, which was put in place to try and prevent some of these spoofed attacks. We'll have a bit more to say about that later. The attack analysis itself will have a in-depth attack analysis on a technical level, look through and demonstrate exactly how this attack happens and what are your options to mitigate such an attack, both from the point of view of not being part of the attack and also for networks if you want to protect yourselves against such attacks. So the first thing we're going to look at is the NTP protocol. The NTP protocol is used to synchronize clocks, computer clocks on your network worldwide with UTC time. So for instance, if you've got job systems or logs that you want to correlate, you want all of the systems to have the same time, and what you would do to have that is use the Network Time Protocol, NTP. The NTP architecture is client-server based, where a client requests time from the NTP daemon, and the NTP daemon gives it the latest UTC time, atomic time to be exact. NTP layer 4 protocol is UDP, so it's a connectionless protocol, does not need to establish a connection with the client. The way NTP works is pretty simple. You do, like we said, you have here the client request from the server, from the NTP server itself. What's the time, and gets a response. Here I've shown a request which is part of our puzzle for this attack, something called the monlist command. Monlist is a command that's in the NTP, it's supported by the NTP daemon, and it will actually list who were the last peers to query the NTP server itself. So if I request a list from the NTP server, say, please can you tell me who has recently requested from you a time, it will send me back all of the servers who have requested it from that one response. There's a client that you can use called NTP DC, which can query the NTP daemon with a mon get list command. We'll have a look more at this more later in the technical demo. So now that we've looked at the NTP, let's have a look at what a reflective and an amplified DDoS attack is. Our malicious attacker over here is going to first send a small request to the servers. Let's say these are the I put DNS here because this kind of scenario can also happen with DNS, which is another connectionless protocol, which is not the focus of this video, but just to demonstrate this can happen with other connectionless protocols. DNS is another very common DDoS attack. But in this case with NTP, what we see is the attacker will send a request, a mon get list request. These servers here will all respond to the request with the response, but instead of responding back to the client, in this case our malicious attacker, the malicious attacker actually sends the request with the source IP spoofed with that of our victim. So the attacker sends a request to the NTP daemons, the NTP servers, all of them here, then all respond to our victim because the attacker put the source IP address of the victim when he sent the original request to the servers. Now, that's the reflective part of this equation, but we said amplified and reflective DDoS attack. So the small request comes. Now, the request is about 200 bytes. We'll see this later, but the response is going to be much larger than the original request, because don't forget, this is a UDP protocol that we were speaking about, and UDP is connectionless, so you don't actually need to do a three-way handshake with all these servers. So the response, the way that the NTP protocol works in this case, is that the response comes straight back to the victim. Now, we spoke about something called best current practices, BCP 38. BCP 38 is a standard that I've put a link here if anybody wants to read in depthly about it, but the gist of it is router 2 here, you can see has behind it network 204.69.207.0. Now, if an attacker were to be sitting here in this router, BCP says that, or an attacker or anyone else for that matter, if you were to be sitting in this subnet of the router, when I send a packet out of this ISP to a router 1 or router 3, my source IP address has to be from 204.69.207.something. If it was from 157.166.248.something, it would be rejected over here on this router with ingress filtering. So the idea being, if we go back quickly to this diagram here, this attacker sitting somewhere in the world had to send through his request to all of these servers. Now, of course, the attacker, number one, it doesn't want to be traced, but in this case, more importantly than being traced is actually you need to have the source IP of the victim for the reflective part of the attack to take place, because the source IP is actually where you put your target. So source IP equals target. So what we have over here is if this router were to block any other source IP other than this network, it would make it impossible for this attack vector to take place with the methodologies used today. So for the NTP attack. So of course, this is a best current practice, which is not loosely followed, but not followed 100%. You can see here, there's a project called the Spoofer project, and it actually measures all of the internet's address spaces and see who complies to the BCP 38 implementation. And we can see here 82% do comply, but the fact is that 33 million network ranges are actually susceptible to having spoofed packets sent from them. So an attacker doesn't have to look that hard to find out where those addresses are, and all he would have to do is place a machine in one of those address spaces to perform the attack. One of this section here, that is. Let's go ahead and have a look at our demo. First, let's look at the environment. We've got your Kali Linux as our attacking machine, and our NTP daemon is running Debian. Our victim machine is also running Debian. If we look at the attacking machine, the IP address that's been assigned is 168.20, 192.168.20. On our Debian victim machine, it's .1.22. And on our NTP daemon itself, it's .21. Let's have a quick look and make sure that we actually are running the daemon here. It should be on UDP port 123, and there you have it. Great. So the environment's ready. Let's just go ahead and verify on our Kali machine that actually we have only one NTP daemon running in the environment, just for sanity's sake. We'll use Nmap to help us do that. Okay. Great. We can see that of our 3-machine environment, only .21, our actual NTP daemon, is running NTP. Okay, now we'll connect to our attacking machine and query the monlist command using our NTP DC client and verify that we actually do get a response. Great. Now we can see that a list of peers that are listed in the NTP daemon are being listed on our attacking machine. That's exactly what we wanted to see. Now, in order to understand what happened when we executed the monlist command, we'll now have to look at the traffic between our 3 servers in Wireshark at the time that the command's executed. So we'll begin Wireshark on all of the servers in our environment. Let's first get it here on our victim machine .22. Next on our NTP daemon. And on our attacking machine. Okay, Wireshark's ready go. Okay, let's go ahead and execute the command again. So this is retrieving a list from our .21 machine. Remember, .21 is our NTP daemon, 192.168.1.21. And as we expect, we're getting a monlist command of all our peers. Great. So the command executed successfully. Let's have a look at this capture and see exactly what happened here. Let's just stop everything first. Okay. On our NTP daemon, we can see this is our .21 machine. We can see that we have 2 packets. We have one packet that is our request packet. You can see the response bit is set to 0 and the request mon get list 1 is there. And our response packet where the response bit is set for our mon get list command. That's exactly what we expected. That's normal behavior. On our victim machine, we don't see anything, which is also expected. And on our attacking machine, we see exactly the same as we see on our NTP daemon .21, and that's also expected. So we see a request and a response. So an important thing to notice here is that the response is 410 bytes, and the request was 234 bytes. So now let's go ahead and spoof the packet that we're going to be sending to the NTP daemon. We'll do that by exporting a packet of the mon get list request command, and we'll then send that packet off to our NTP daemon, which should respond to our victim on .22. So right now we exported this packet here. You can see it's got .20, which is right now our attacking machine. We want to go ahead and change that to .22. Let's just make sure that verify our IP again. Yeah, our IP of our victim is .22. So right now, what we need to do is send our spoofed packet to our NTP daemon listening, and that spoofed packet has to now have a source IP of .22. So our mon list request command needs to have a new source IP so that we can relay that packet, reflect that packet back to .22. So what we want to happen is we're going to send the packet from our attacking machine 192.168.1.20 to our NTP daemon on 192.168.1.21. And we hope that our response from our NTP daemon of over 400 bytes will go back to our victim waiting on .22. And remember, our request is only 230 so bytes, and our response is over 400 bytes. So remember, if you were with BCP 38 in the wild, this wouldn't work, because the best current practices, you are not allowed to send a spoof packet out of the net. Let's verify that our TCP rewrite command actually worked and that there's been an issue with the checksum. Great. We see that we have here our .22 packet. We can say so we've successfully spoofed a packet with our monlist request command. We're going to send now to our victim via our NTP daemon. We hope that's what's going to happen. We're going to try and replay the packet from our attacker to our listening NTP daemon, which should send a response to our victim. Let's just get Wireshark started up here on all of our machines so we can follow the traffic flow again. Let's see how this works. Great, so now from our attacking machine, we will use TCP replay to loop the packet 5 times to our waiting NTP daemon on 192.168.1.21. Great, we can see in the background immediately that 5 packets were sent with our monolith. You can see the source IP is .22 here. And those packets all are 234 bytes in length. On our victim server, we can see straight away that there is no .20 IP in our source range. And on our NTP daemon, we can see that we have a IP set of 21 and 22. We don't have any .20 here. There's also, so that's because we sent the request from our .20 with a spoofed IP of .22. And on our attacker, we see our source IP is .22. That's what we expect. That's our spoofed packet, which is the destination IP that we wanted to have our NTP daemon sent to, .22. So let's filter on our NTP daemon itself. Let's filter out for our victim packets, which are 192.168.1.22. And then we'll be able to understand a little bit better what happened here. So here on our NTP daemon, we can see that our first request comes from .22, which is our victim machine. That's the spoofed packet. The response then will go to our back to our .22 from 21 to 22. There's the response. And you can see that the response is 410 bytes and the request is 234 bytes. So it's almost double. You also see here these ICMP type 3 packets, which are 438 bytes. That's because our NTP daemon sends to a port that isn't open here on our victim server on UDP port 123. Of course, there is no port 123. So that's why they are sending back these ICMP type 3 packets. And those are also saturating upstream bandwidth with 438 bytes. In this case, that will vary. It will obviously depend how many peers are in the monolith command to how big the response will be and also how big the ICMP type 3 packet will be. Now what we'll do is let's have a look at a real NTP daemon on the internet that I located, and we'll see how large a response really is in the wild. Here we only had a factor of 2. So our request was 230 bytes and our response was 430. So it's almost double, but let's have a look at a real server. And here we type our monolith command. The first request seems to have timed out. Let's send it again. Great, so this time it executed. Now let's go and have a look at our Wireshark. Let's go ahead and see what happened. We can see here a lot more packets. Look at that. We can see all of these are the same source, the source of our NTP daemon, and only a single source from our attacking machine. So you can see there, it's still loading, but in our Wireshark the data has already been transferred. That's probably because of the resolving, I'm not sure why, but we can see nevertheless a single packet generated 192 packets in the response. No verification, nothing. So this is how this attack actually works. This asynchronous communication allowed a reflective attack vector to take place, and this amplification of 192 packets. Let's have a look at how much that actually is in terms of how much the attack was amplified. But we can see here that our request was 234 bytes. Each response is 434 bytes. Sorry, 482 bytes. So that's 90K response. 90K from a 230 byte packet. That's a amplification of 395 times. I hope that this demo gave you some insight into how this NTP attack vector works. You could see it's a classic massive volumetric attack. It's very clever how they are utilizing the NTP protocol to generate these DDoS attacks. It's happening every day. You can see that there's 300, 400, 500 gigabit attacks. It's real. It's happening all the time. And you can see that just by generating a small request to listening NTP daemons with this asynchronous communication, it straight away sent back a much larger response to our unsuspecting victim. And in the wild, if you had a few thousand of these NTP daemons, you would be able to very quickly generate a large attack with a minimal amount of resources as an attacker. So let's look at the mitigation aspect. I look at the mitigation aspect as a two-pronged approach. Number one, how not to be part of the attack. And number two, what do you do if you do become part of such an attack campaign against your network or infrastructure or website? So don't be part of the problem. You need to update your NTP daemon if you don't want to be used in this attack vector. If you don't want to be one of the participants, update your NTP daemons, and by default the monolith command has been disabled. If you don't want to update your NTP daemons, just disable the monolith command. I'm not sure exactly why you need the monolith command nowadays. Some people say they use it for enumerating the network, their network nodes, because it gives you back a list of peers. That's actually was the only information I was able to find about anybody who is using this command for anything practical. If someone could write a comment and tell me that they are using that in a practical sense and why they're using it, it would be interesting to know. But anyway, a new command, MRU list command, was released, and that uses a nonce to avoid the spoofing vector of the attack. And once you've made the changes, verify the changes worked by just executing your own monolith command from an NTPDC daemon or any other NTP client. And if you go to team-cymru.org, they've got a very interesting article on how to secure your NTP setup in a whole lot of different environments with different servers that you run in BSD, Linux. And I would recommend going to read it if you are going to take action to secure your NTP daemons in your network. If you want to mitigate an attack targeting you, you have a couple of options. If the attack is smaller, you could use CPE equipment, customer premises equipment. There's a few vendors that provide hardware that can mitigate such an attack. The problem is even if your CPE equipment is the best equipment in the market and does the job that the vendor promises, the problem comes when you get a 300 or 400 gigabit attack. I don't know many networks that can sustain a 300 or 400 gigabit attack, so that's when you need to start looking at cloud providers and what the SLA would be on that. Most cloud providers who deal with DDoS attacks would pretty easily be able to mitigate technically such an attack. The provider would need to be big enough, but the attack itself with the right equipment is not such a problem because it's very noisy, it's very clear. It's very clear what type of attack it is. It's very distinct traffic. So those are your two options. You've either got to go with a cloud provider or you've got to have a CP equipment, but your safest is a combination of both, because your cloud provider may miss some of the traffic and you'd use the CP equipment to clean it off. And of course, you're not only dealing with NTP attack vectors. So generally, the bigger guys in the enterprise environments, you guys want to have a combination of both CPE and cloud provider services. The cloud provider would classically take this 300 or 400 gigabit hit. But when you have those multi-vector attacks coming towards you with DNS and NTP and all the application TCP layer attacks to your web services, then you definitely want a combination of both cloud and customer premises equipment to manage the attack. The reason is simple, because when you come under a sustained attack campaign that you see sometimes, not as in, there was one in America, Operation Upper Bill, where they attack the banks for months at a time, and these attacks are happening everywhere, not just in the States, in Europe. You could see that the attackers are actually very quickly adapting to your mitigation strategy, and it's not a pure volumetric attack. Now, a cloud provider doesn't necessarily know your network well, so if they start trying to mitigate these more granular attacks on the application layer, they may start actually becoming part of the denial of service, because they aren't sure how your backend applications work, and actually you need a vendor that really knows what they're doing to assist you with your CPE equipment to mitigate such an attack. From Mazebolt, I hope you gain some understanding of how the NTP DDoS attack vector works. I hope it will assist you in improving your security posture, in defending your network. If you have any questions or comments, please leave a comment below, and we'd be happy to get back to you as soon as we can. Thank you. Bye-bye.